This is a question from the 2004 Maths Paper 1, question 6c. So we're dealing with a calculus question, namely differentiation, and linking in with a bit of functions here, where we actually have to complete the square. We don't have to use the completing square method for this part when we want to write it in this form. We can also use the comparison method, where we actually multiply this all out and compare our a, b, and c to our form to ax squared plus bx plus c. We can compare it to that. But for this video here, I'm actually just going to use the completing the square form. So part ci, we want to basically just differentiate this function here. That's quite straightforward. So we're going to differentiate by rule. So when we differentiate by rule, we bring down the power and we reduce the power by 1. So if I differentiate x cubed, I get 3x squared. If I differentiate 6x squared, I get 12x plus 15. And then if I differentiate a constant, which is our 36 here, I'll just get 0. So we found our first derivative here. Now we want to write it in this form here. So if you think back to completing the square, the most important thing is that the coefficient of the x squared has to be 1. So basically nothing in front of it. So we're going to factorize out the 3, and then we'll have x squared plus 4x plus 5 on the inside. Now we're just going to ignore the 3 for the time being and focus on what we have inside the bracket here. So when we complete the square, we divide the x coefficient by 2, and then we square it, and then we add it on. So x squared plus 4x, I divide 4 by 2 and I square it, and I get plus 4. Now, remember, we're dealing with an expression here. So with an expression, and we want to rewrite it in form, the important thing to note is that we're not trying to change the value of it, and we shouldn't change the value of it. We're just trying to change it from one form to another. So we're simply just changing what it looks like. So if I'm adding on 4, I also need to subtract 4, because now I'm not really changing the value of it. I'm just changing how it looks. So when I complete the square, I essentially group my terms like this. Now, this first part, if I complete the square for it, I'll get x plus 2 squared. And then I could just add these two together, and I'll get plus 1. And then don't forget, the 3 needs to be on the outside. Now, that's the first part done. So we want to look at part 2 now. Hence, show that f of x is equal to 0 has only one real root. The first thing looking at this question, a lot of students would actually not read it properly. It's important that they're saying that f of x is equal to 0. So it's actually the original function, not the derivative. So we actually need to refer back to the original function. But the problem is, we don't know just by looking at this that there is one real root. I mean, you could use the factor theorem and try to find the factors and hence the roots. But that's not what we want to do. We want to use our part 2. So now, if you think about our part 2, our derivative is this here. And when we rewrite it in completing the square form, we get this form here. So remember that our derivative is essentially telling us whether a function is increasing or decreasing. Now, if we look at this, we can't really infer whether it's increasing or decreasing. But in this form, we know that this strictly has to be greater than 0, which means that it's increasing for all of x. Now, why is this greater than 0? Well, think about my x values that I can put in. If I put in, say, a positive number, it's always going to be positive, right? Because I'll get a positive number here, plus 1, it's going to be positive, multiplied by positive 3, plus 3, it'll be positive. Even if I put in something that's less than 2, so say minus 3, now any number squared is obviously positive. So no matter what I put in for x, this part will always be positive. So we can say that 3 by x plus 2 squared, so the function f prime of x, is greater than 0 for all x, which implies that f of x is an increasing function. Now, when we're talking about an increasing function, we're talking about this one here. So if you think about this function constantly increasing, it's not going to come back down again, right? So you can imagine if I had some sort of cubic function, right? It's increasing always, right? Meaning it's going to go up here, 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 going up, up, up. It's never going to cross the x-axis again, right? So it's only going to cross the x-axis for one point. So therefore we can conclude from that that there is only one real root.